Okay, so range, starting with number 18. So this says to find the range of the function. So we've got g of x is equal to 5 plus the square root of 4 minus x. So in general, we haven't done this yet because it's the next section. I kind of wish they taught these sections in reverse, but the next section is the parent functions. And so what you would see is that the graph of a square root function looks something like this. Okay, and it keeps going. So the range of, in general, a square root function would be 0 to infinity. But this one is being shifted and reflected and, you know, all the things. And the principles that we had when we did, like, parabolas and what happened with the stuff that's inside the parentheses, kind of the same thing. If it's inside the radical, it does the same thing. Outside, you know, is up and down. So inside is left and right, outside is up and down, and then, you know, reflected and such like that. So, but we're going to just graph it on our calculator for the sake of one time and two, you know, just making it easier. If you ever have something that you don't know what the graph looks like, this is the easiest way to do it. So what y equals, hold on, I gotta turn, Josh, you may need to turn a stat plot off on your calculator if you have them on, because otherwise it'll cause a problem. So then you just type it in as it is, so 5 plus the square root of 4 minus x. X is up here. And then zoom 6 for zoom standard once you have it all typed in. So this graph basically was shifted up 5, okay? And I don't really care about anything else because I'm only caring about the range, but I just want you to be able to see it. So this was shifted up 5, and so this was reflected the opposite way. If the negative was outside the radical, it would be different. It would have flipped it over, I'm pretty sure. Anyways, so it basically flipped it from this way to this way, and then it shifted it up 5, and it technically went right 4, I think. Yeah, something like that. Anyways, so up there like that. So my range is going to be from 5 included to infinity. And then something like 20. And I'm just going to go ahead and tell you with something like 20, I don't even know what the graph of it looks like just off the top of my head. I know what a lot of graphs generally look like off the top of my head. This is not one of them. So again, we'll type this in, so y equals, and don't forget if you hit alpha and then y equals, it brings up the option to type in a fraction, just so you can make sure you don't have to worry about parentheses and stuff. So alpha y equals, and then just hit enter. It should say like n over d for numerator over denominator. And then once you have it typed in, it'll be zoom 6 again.
That's fun.
It looks like a little person going down.
Yeah, it does kind of. So this one, it's kind of hard to tell, you know, what, the range is just by looking at it, especially with this one. It kind of looks like it's probably going to -1 and like stopping potentially. Actually, we can decide because horizontal asymptotes will tell us if it's going to cross it or not. So would I have a horizontal asymptote on this one? Okay, so horizontal asymptote, all I care about is, let me move this for a second, is this part right here. Oops. Okay, normally it's in the front. In this case, it's not. So all I care about is this part right here. If they're both the same, so this is going to be Bosco, okay, it's the coefficient. Okay, so back from your clown poem. It's the coefficient, so it's the numbers in front. So I've got a +1 over a -1. So that tells me that I'm going to have a horizontal asymptote at y is equal to -1. Okay, so that tells me that since I know I have a horizontal asymptote at -1, I know that my range is going to stop there, and it's not going to include -1. Okay, so going back to my graph really fast. So I'm from -1, and it looks like I'm going all the way down. I should assume, I mean, I can't see it, but I should assume it's going all the way down. So this is going to be, the first part is going to be -infinity to -1, not including. So -infinity to -1. Union. Now the top part, I don't really know what it is, and so I'm gonna hit trace. Okay, so that's this button up here, and I can actually just follow this graph around, and I'm trying to see what the lowest point is. So the lowest point here is on my vertex, and it's at 3/4 or 0.75. Okay, you see that? So you can go around and you can see it, you know, move it around, make sure, but my lowest point there is at, well, on the X or on the Y axis. So that is going to be then, so the union part, and it's going to be including because it's on there, so 0.75 to infinity because it looks like it's going to go on up forever. Any questions about that? So you don't need to really be that stressed out about range at this point. We do a lot more with range in calculus. This is kind of like a just get to know it, you know, be able to look at a graph and see and whatever. And let's say you didn't know, like at this point we didn't know horizontal asymptotes. You could use the trace function on the other chunk of the graph. If you just arrow over long enough, it'll move it over. And it would just keep getting closer and closer to -1, but it would never quite get there, and so you would just make an assumption then at that point that it's at -1. All right, we okay with range for now? All right. So then the next thing is graph the function and tell whether or not it has a point of discontinuity at x equals 0. If there is a discontinuity, tell whether it's removable or non-removable. So we'll graph these ones on our calculator as well. So 22 h of x is equal to x cubed plus x over x. So basically, I'm trying to see if at x equals 0, there's a problem. Okay, so we're going to plug that into y equals again. So x cubed and I think y'all probably remember, but there's not like a cubed button on the calculator directly. Well, there might be under math, but anyways, but if you hit the little caret button on the right hand side, it's a little arrow, that does it for you. So. And then zoom 6. Did you figure it out?
Yeah.
All right, so now I can't see. I care about what's happening at x equals 0 because that's what they asked us to check. So I'm going to zoom box. So that's the first option. And so I'm going to come down just below the axis. So I just arrow down, arrow to the left. Use this little star thing here. Hit enter, arrow up. And you don't need to go super far up, just a little bit above the graph. Above this x equals 0 point, and then you just arrow over, and so it makes a little box like that. And then once you have it boxed, you hit enter. And then I'm going to trace it and see basically what's happening here.
How did you box it?
I hit zoom and then box, and then, hold on, let me go back. I'll do it again. So zoom, oops, zoom box, and then I arrow down a little bit below, and then to the left to like -1-ish. You hit enter, and then you arrow up to where you want it, and then just to the right, and it makes a box. And you can do it the other way and do it like to the left instead, but.
And then we just hit trace or second trace.
Just trace.
Okay.
And so this one, it's kind of hard to see in the graph. I was thinking it was going to actually show it to you, but it didn't, because this problem, this can be reduced down, and so the graph isn't really showing it to you. But we would have a point of discontinuity at x equals 0, because if I plug in 0, that gives me a 0 in the denominator, which is a problem. Now it's going to end up giving me 0 over 0. But because it can technically be reduced down, it's going to be removable discontinuity. So this isn't like the best example in the world. I was hoping this one would be a little bit better, but it wasn't. So hold on. So this one would be discontinuous at x equals 0, and it is removable because the point does end up getting filled in.
Does it matter if I got different numbers after I traced it to my x and y? Like, my numbers were very different. I got x equals 5 and then y equals 1.
What do you mean?
For that part right there. Maybe I didn't like.
I'm just you just move it around.
I don't even see my point.
Well, every time you arrow, it should change the numbers. And if you're getting x equals 5, you aren't zoomed in as far as I am, because I'm zoomed in from like -1 to 1.
I hit the up arrow and then it appeared.
Oh.
I don't know where it went. And then like everything turned blue because everything was pink.
Okay, hold on. I remember what I needed to show you and how you would see it. So we can't see directly that there's something wrong here, but if you hit second trace, okay, so I know I'm probably confusing you, but second trace and then value, then you type in x equals 0 because that's what we care about. I just don't use these functions very often, so I forget about them. Hit x equals 0, hit enter. See how it comes up with a blank y? That tells you when x is 0, there's no y value. So that tells us that there's a point of discontinuity there. And that's why we would know that.
So I got lost.
Okay.
And I'm on the part where just after we made the box and then I pressed enter, so it's like zoomed in now. Yeah, there.
So you're just there?
Yeah.
So yours looks like that right now?
Yeah.
Okay, so I had originally said just to trace it, so just to hit the trace button and go along, and now I'm realizing as I'm arrowing that my X values never actually hit 0, and realistically when I'm going along my graph, I should have a point when X is 0, just arrowing, that it should hit it, but I'm not seeing that, so I was like, let me see. So I hit second trace, which is the calculate option. In value, when you plug in a value for X, it'll tell you what Y is. So I did that. It says X equals, I plug in 0, and again, that's because that's what the instructions say. If it gave us a different number, I could plug in a different number. And then I hit enter, and so it comes up and says when X is 0, Y is blank, okay, which tells me there's discontinuity there. Because I can't have a 0 in that function that was given to me. Even though it can be reduced, there's still a problem. So that's why it's removable, because I can get it simplified down to there's a value that goes there. However, like the point would actually end up being like right here. The point where the removable point would end up being.
Yeah.
But because I can reduce it down, it will be removable. But this one is discontinuity because of that. Let's look at one more like that. 24, g of x is equal to x over x minus 2. So, we're going to type this in again. Over x minus 2. And then because you had just been zoomed in on that box, make sure you hit zoom standard again. And so this is what I got. So I only care about right now. Now, I'm going to tell you that this function is not continuous because it's split like that. This is what we would call an infinite discontinuity. We don't care about that this year. Next year we'll care about that. But anyways. So I just want to know if there's a point of discontinuity at x equals 0. Okay, it's not asking if the whole function is continuous. It's just asking at that point. So I don't even, at this point, I'm not even going to zoom in. I'm just going to hit second trace calc, and that'll just honestly give it to me faster. You can zoom in if you want to like look at it, but you don't have to. So again, x equals 0. And it tells me at x equals 0, y equals 0, so I know that it is continuous at x equals 0. Because there's actually a value for y when I put in x is 0. So this one would be continuous at x equals 0. But the function as a whole is not continuous because we have a vertical asymptote here because 2 is a problem. And so in my domain, I would have to remove 2 from my domain because that would cause a problem.
When you went to second trace, did you press value?
Yeah.
So how do you know again if it's removable or not?
So basically, I was able to reduce this down. So like, I was able to take this and basically factor out an x. So I had x times x squared plus 1 over x, and I was able to get rid of the x's. So x squared plus 1, I was able to basically fill in that hole by graphing this.
Okay.
So it ends up giving me like a spot that we can put, like a value that we can put in. I was trying to think. There's only like, it's kind of annoying because they only give you 4 problems in this section. So I was trying to look and see, but there's not an even one that is non-removable. I don't know. I'd have to find an example to show you what that would actually look like. But basically removable means like when you graph it, so this isn't going to be for any of these examples, but basically we graph a function, there's a hole here, and then it can be filled somewhere else. Like on that same x value, it's getting filled. So it's, and then non-removable would just, there would just be a hole with nothing, like nothing filled in. So then that would be removable. This would be non-removable because there's nothing that can fill it, basically fill that value.
So the one we just did would also be removable?
Well, so this one's continuous, so it's neither.
Okay.
So it's only removable or non-removable if it's not continuous at the point.
When I did second trace, it said I have to give an x value. What should I put in for that? Because it doesn't just come up as like x equals 0. Like, you know, at the bottom of it.
When you did second trace and then value,
Yeah.
it didn't.
Yeah, that.
It didn't give you this.
What did you just press enter?
I just pushed 0 and then I'm gonna push enter.
Okay, now it does.
Now it does. Okay, just making sure.
I thought I pressed the wrong button somewhere along the way.
Okay. So that's all for that part. What's next? There's some stuff we may go back and look at later because I mean there's no point in me trying to put it up here because you won't be able to see it in the video, so we'll just look at that later, some pictures for increasing and decreasing and max and mins and stuff, but we're not going to look at that right now. The next step is determine whether the function is bounded above, below, or bounded on its domain. So 36 y equals 2 minus x squared. So this isn't written like we normally would see, you know, a parabola written, but we can rewrite it ourselves as y equals negative x squared plus 2. And so I don't really care about how it's being shifted. All I really care about is if it's being reflected or not. So a parabola, we ordinarily know looks like this, right? It makes a U. But if it's reflected, what happens to it?
It's like upside down.
Yeah, it flips upside down. And so basically we go from it looking like this to looking like this, right? So bounded, I'm looking at, is there a part that is like basically making it a max that I can't go above or a min that I can't go below? Okay, or sometimes it can be bounded on its domain and that's something different. But so this one, okay, it has basically a max point. It can't go higher than this point right here. So this one is going to be bounded above. And that's all these questions are asking you for, is to tell if it's bounded above, below, or on its domain. And I will tell you some functions are not bounded above or below. So like the function that we did, this one technically is not. Or wait, hold on. Yeah, that one wouldn't be bounded. Let's look at 38. So 38 is going to be one where you probably aren't going to know off the top of your head what that looks like. A parabola, we know, we're good to go. But this function, you may not know exactly what it looks like. I mean, we probably generally know what an exponential looks like, but that negative exponent, that's causing a reflection, and you may or may not know how that's being reflected. So, go to your calculator again to y equals, and we're going to put in 2 raised to the negative x. Now make sure you use the negative sign at the bottom of your calculator, not the minus sign, or it'll cause a domain error. And then zoom 6 again. So basically, this graph is hitting and it's coming down. Now, it's not crossing there. It's stopping, or at least it looks like it. We can trace it and find out. So I'm going So basically what this is telling me is y is getting really close to 0, but it's not actually hitting 0, so I know that it's basically being stopped, okay, which means it's being bounded. So this one is going to be bounded below, okay, because it kind of looks like it's saying, oh, it's 4 point whatever, but it's to the negative fourth, so that would mean it's like 0.0004, blah, 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 blah. Y'all see that? See what I'm saying? Basically, it's like there's an asymptote that we can't cross that because it's going to end up causing a problem. So this one is going to be bounded below. Let's see, 40 y equals x minus x cubed. So again, we might kind of have a general idea of what this looks like. And also, just hypothetically, if you got to the AP exam and they said, sorry, no calculator on this part, you could just plot points. You could just plug in different values for x and try to figure out what's happening based on that. I would, takes longer, but you could do it without a calculator. That way, if you don't know what this looks like. I know what a cubic function looks like, but having that one, it's going to be reflected because of the negative sign, and then also with that x on there, it's hard to know exactly what that's going to look like. So I'm going to graph it. So I've got x minus x cubed and zoom 6. So actually looks relatively similar to what a cubic function looks like. It didn't change a whole lot with that extra x on there, and it's just been reflected because a cubic function in general looks something like this. Kind of looks like a tangent function. They're slightly different, but they kind of look the same. So basically, this is going all the way up to infinity, and this is going all the way down to negative infinity. So this one is not bounded, okay? Not bounded above or below because there's nothing stopping it. It's going all the way out to infinity in both directions. And then just one more that I want to just show you because they don't have another example like this in the book, but one that's bounded in general on its domain. Let's do the square root of 4 minus x squared. So we know what the square root function looks like, right? But with that negative on it and there being squared in there, we should probably graph it just to make sure we know what's happening. Whoa, apparently my iPad doesn't know what's happening. Just freaks out. There we go. So I'm going to type this one in. Square root of 4 minus x squared. Zoom 6. So definitely not what a square root function looks like, right? So it's a good thing we graphed it. So basically, we can't have anything negative under the radical, right? So we're limited to whatever would make this be 0 to positive infinity, because I can't have anything negative. But this is kind of like the problem. I think we did the domain for something like this previously. If I set this stuff greater than or equal to 0, I'm going to end up basically saying that x can be positive or negative 2 and anything in between, but it can't be bigger than that because that's going to cause a problem under here, right? Because if I plug in 3 squared is 9, 4 minus 9 is negative 5. That's a problem. So I basically have a domain of negative 2 to 2, okay? And so what we would say then is that this is bounded on its whole domain. So this would be, the book is just going to say bounded. If it just says bounded, that means it's bounded above and below, okay? So in this case, it's bounded on its domain, which would be negative 2 to 2, because it can't go below the x-axis, and it's only going up to whatever that is, 2 on the y. And so we can tell just by looking at it, it's bounded above. You kind of have to look at the domain to know that it's also bounded below. So this one would be one that we classify as bounded on its domain. Okay. So the last stuff we have in this section is telling if a function is odd, even, or neither, and then finding horizontal and vertical asymptotes. So none of that's super hard. We don't have enough time to do it today, though, so I'm going to save those two things for tomorrow. But what I'm going to do is go ahead and give you the problems up to this point. This section is probably going to have more than likely the most problems you have all year, just because this is a really long section that, to be completely honest, should be like probably 3 to 4 days of separate material. So, like if you hadn't done those notes at home, or like, you know, it would have taken like a whole extra day. Like this section could be taught over a week. So, at this point, we've got, I don't think I gave you any last week at all, so I'm just going to put them here. 1 through 11 odd. Then we've got 17, 19, 21, 25, 35, 37, and 39. And what I would say is I'm going to be adding 1, 2, 3, 4, 5, 6, 7, 7 more problems. It shouldn't take us super long to get through them tomorrow, because I think y'all will pick up on that stuff pretty fast probably. Not necessarily that we've done it before, but I just think that you'll pick it up pretty fast. What I'm going to say is, especially for the stuff that's like, you know, like 1 through 11 or whatever, once you've got the topic down, if you feel like you've got it, this will be the one section where I'll say you don't have to do every problem that I've given you. Okay? I've tried to go through and pick as many as I could that are, you know, good practice for you, but I've also tried to do a decent amount for you so that you have more examples, because this tends to be one of the harder sections for people to understand. Sometimes it doesn't matter how long I spend on it, it still ends up being a problem. So, also, you actually can't do 25 quite yet. You'll have to wait till I do the thing where I show you what's happening. So just hold off on 25, but you can do everything else at this point. Don't have to do it all. It'll all be due the same time. But anyways, I'd figure y'all might want to get a jump start on it since it's a big section.